So we know that when we have a dependent variable that is a dummy variable, and we have explanatory variables which we think affect the dependent variable, then one choice is to do the linear probability model. But we have also talked about the problems and the limitations of the linear probability model. In particularly, the problem of predicting probabilities that y is equal to 1, which is outside the 0-1 bound, but also the problem of having a constant marginal effect. So what we will try to do in this lecture is to try to amend the problem in the linear probability model, and this will lead us to the binary choice models. So let's start with a very simple case where yi, our dependent variable, is a dummy variable, and we only have one explanatory variable. The linear probability model, remember, it assumed that the expected value of y conditionally on x, just working with an arbitrary observation, was beta 1 plus beta 2x. And we also concluded that this expected value was the same as the probability, so we can also write it like this. The probability that y is equal to 1 conditionally on x is this beta 1 plus beta 2x. And the problem, of course, with this model is that that's a linear function like this. So if I put the probability here and x on this axis, and let's say I have a 1 here, then as soon as I go outside and put large values of x, it will predict the probability that's greater than 1. And whenever I use very small x, this is assuming that beta 2 is positive, by the way, then I will predict a negative probability. So the fix in the binary choice model is actually pretty straightforward. This part here, we're going to call that zeta, the Greek character zeta. So zeta will be defined as beta 1 plus beta 2x. Then what we do in the binary choice model is that we model this probability not as beta 1 plus beta 2x, but as some function of this zeta. This will make the model nonlinear, so the probability will now depend non-linearly on x and on zeta. And if we impose the restriction on f that f has a range which is 0 to 1, actually not including 0 and 1, then this value will never be outside 0, 1. There are several such functions that satisfy this condition, and we will look at some of them in a second. But just to summarize what we have said so far, so what we are doing is we have now a more general setup where I have a random sample. My dependent variable is a dummy variable. We can generalize this to more than one explanatory variable. So then we just define this zeta I simply as this linear function of all my explanatory variables. So the x data is observed, the beta parameters are unknown, and the zeta value is unknown as well. This zeta parameter or zeta value is important in binary choice models, but it's important then to point out that we do not assume that the probability that yi is equal to 1 conditionally on xi is zeta I. That's exactly what we do in the linear probability model. And that is what is causing the problem for the linear probability model, because linear functions are not bounded to lie between 0 and 1. So instead, we move to the binary choice model and we assume that this probability is instead a function of the zeta value, not zeta itself. It's a function of the zeta value. So all the zetas are mapped by f to, to a value that strictly lies between 0 and 1. F is strictly increasing because we still want this feature of the model that the bigger this linear function of the x variables is, the higher is the probability. And like we said, there are actually many choices of such a function. The function must have as a domain all of the real numbers, and it must have as its codomain or range the open interval 0 to 1. So you can think of binary choice models as a whole class of models containing a whole bunch of models. And what separates them is simply the choice for f. So the name of the model will then be based on which choice we make for f. In this lecture, we will only discuss two choices for f, the two most common choices, and these two choices will lead to models that are called the Probit model and the logit model. So I think the simplest function that you can pick for f is the following function called a logistic function. So let's have a quick look at the logistic function. F of x is 1 over 1 plus e to the minus x. So first, just a reminder, the natural exponential function e to the x looks something like this. This is e to the x. It's strictly positive and strictly increasing, and for x equal to 0 it's e to the 0, so it's 1, so it passes through 1 here. E to the minus x is the reflection in the y-axis. So e to the minus x looks like this. This is e to the minus x. So if we look at this logistic function, we can see that f of 0 is, plug in 0 here, you get 1. So 1 over 1 plus 1, so it's 1 half. Then, as x increases from 0, e to the minus x, you can see here, will decrease. And if this part decreases, the f value will increase. But you can also see that e to the minus x is never negative. So the smallest value e to the minus x can take is, well, it can't really take 0, but it can get arbitrarily close to 0. And when e to the minus x is almost 0, f will be almost 1. So it increases, but f of x is always less than equal to 1. It gets closer and closer to 1. If we go the other direction from 0, and we take x down from 0, moving in this direction, e to the minus x will increase. So e to the minus x will increase, and that will mean that f will decrease. E to the minus x will increase with no bound, so it can be as large as you like. But since both of these are positive, f can never go below 0. Actually, we can even scratch these guys because f can never become 1 and it can never become 0. So put together, the logistic function looks something like this. 1 here, 1 half here. It goes like this, through 1 half, and then like this. This is the logistic function. And it has the properties that we are looking for the binary choice model. So when we use this function, we say that we are working with the logistic model or the logit model. Another popular choice of binary choice model is to pick f of x to be the CDF of the standard normal distribution. Now, the CDF cannot be expressed using normal functions, but if you make a plot of it, you'll see that it has a shape that's fairly similar to the logistic one, strictly increasing and always between 0 and 1, and it cuts through the y-axis at 1/2. But they are not the same. That's important to note. So once we have set up a model, binary choice model, and made our choice for f to go Probit or logit, we can actually estimate the parameters of this model, the beta parameters. These will be estimated with a very general statistical method called the maximum likelihood. Using this method, we can also find consistent estimates of the standard errors, which will allow us to do inference in the model. So finally, let me just point out that binary choice models are not regression models. We do not specify them as a regression model. Remember, regression model is a model where y is some function of the data and parameters plus an additive error term. What we do instead in binary choice models is that we set up a model for the probability that y is equal to 1. And we set that up to be either a logit or a probit. So finally, let's have a look at how to estimate binary choice models in Gretel. So here, this is my dependent dummy variable, and it's 1 if the student passes the final exam, otherwise it's 0. So if I want to do a binary choice estimation, I go with model and then limited dependent variable. Then I pick logit or probit. So let's begin by picking logit. That's when the f function is the logistic function. You pick finally binary here. Your dependent variable is the dummy variable pass, and let's say we use this 3 explanatory variable. We can click OK and it will estimate the parameters. Again, keep in mind it's not the linear regression model, so these are not the marginal effects of SATV and SATM and so on. Exactly what they are, how they are interpreted, and how to analyze the model, we'll discuss that in the next lecture. If you want to do Probit instead, you go model, limited dependent, Probit, and then binary. And then you do exactly the same thing, and you can see that that will not give you the same answers. As a matter of fact, the interpretation of these parameters are actually different. We'll come back to that. In eViews, you can go to quick estimate equation. Here in the method you pick binary choice, and then you pick Probit logit, and it also has a third choice, extreme value, which is just a third choice for this capital F function. So if you want to do Probit, then you just type the variables just as we always do. So you can type pass, C, and SATM, SATV, HSGPA, and it will give you the Probit estimates. You can see that Gretel and eViews completely almost agree on the estimates of the Probit model.